Thank you for watching this video. My name is Yotam Dikstein, and I'm going to tell you about a new construction of high-dimensional expanders that come from simplicial covers. Let's start. So, what are high-dimensional expanders? A high-dimensional expander is an expander graph that has this extra property that for every vertex in the graph, its neighborhood is also itself a small expander graph. We will see a description of expander graphs, however, using hypergraphs in the next slides. Today we're going to talk about construction of high-dimensional expanders, and I should mention that constructing high-dimensional expanders should look harder than construction of expanders. So what are expander graphs? Expander graphs are graphs that are well connected. A proxy to this is the second largest eigenvalue definition. So for a graph G, we can denote by lambda G the second largest eigenvalue of its normalized adjacency operator. And for some beta between 0 and 1, we say that G is a beta expander if the second largest eigenvalue is less or equal to beta. So for beta equals 1, this is trivial. This just happens for all graphs. But as beta gets smaller and smaller, our graph will approximate the complete graph. This is a very nice definition because it sort of allows us to approximate the complete graph in many interesting ways, while G could maybe be a sparse graph. Expander graphs have been extremely useful in all TCS and in many areas of math too. And one of the reasons for this is that we can so easily construct and manipulate expander graphs. In particular, for every constant beta greater than 0, we can find an infinite family of beta expanders that are also uniformly bounded degree, namely that there is a bound on the degree of every vertex in every graph here. These constructions come from many sources, from group theory, from random graphs, and there are also many elementary or algorithmic constructions of these. To define high-dimensional expanders, we will use the convenient language of simplicial complexes. A simplicial complex is just a hypergraph. A two-dimensional simplicial complex is a hypergraph that has vertices, edges, and triangles. And we say this hypergraph is a simplicial complex if it has the downwards closure property. Namely, if I have a triangle in this simplicial complex UVW, then all the edges inside the triangle should also participate in the simplicial complex, and of course all the vertices. So here's an example of a simplicial complex, and note that when we draw this 3-cycle BCE without filling in the triangle, this means that this triangle BCE does not participate in the simplicial complex. Before, we talked about neighborhoods of vertices. So the simplicial complex will allow us a more flexible definition of a neighborhood, which we call a link. So for a simplicial complex X, a link of a vertex U is just a graph where the vertices in this graph correspond to edges adjacent to this U, and the edges in the graph correspond to triangles adjacent to this U. So for example, if we look at this vertex B here, its link has 4 vertices A, C, D, and E for the 4 edges that are connected to B, and it has 2 edges, AC and DE, for the 2 triangles connected to B. Note that CE is an edge in the global simplicial complex, but from B's perspective, it doesn't appear. If we wanted it to appear, we should have put in this extra triangle in the middle. A high-dimensional expander is the following. A connected simplicial complex X is called a beta high-dimensional expander if, for every vertex, the link of that vertex is itself a beta expander. Note that beforehand, we also required global expansion from this simplicial complex. However, one can show that if all the links are beta expanders and the simplicial complex is connected, then a theorem of Isao-Oppenheim says that this underlying graph of X will also itself be a quite good expander. We should note that the definition of high-dimensional expanders also extends to simplicial complexes of arbitrary dimension, but for simplicity we will stick to the two-dimensional case, which is what's written here. One example for a high-dimensional expander is just a complete complex. This is a set of n vertices with all possible edges and triangles. One can observe that every link in the complete complex actually looks like the complete graph with n-1 vertices. However, as in the usual graph expander case, we care about bounded degree constructions, namely families of these high-dimensional expanders where the size of the links, or the number of edges connected to a vertex in the underlying graph, is uniformly bounded by some constant. Previous to this work, there were two well-known constructions to high-dimensional expanders that also had bounded degree. These came from quotients of the Brouillard building and complexes of groups. Why do we care about high-dimensional expanders? Well, one motivation is that, similar to the graph case, when we take beta to be very close to 0, our simplicial complex will resemble the complete complex in many interesting ways. This has been applied for many things. So, for example, it turns out that you can do Fourier analysis on high-dimensional expanders in a very similar way that you can do to the complete complex. Also, this has been used to de-randomize many things that we were used to doing in the complete complex, such as direct product testing and other property testing. Another reason that we care about high-dimensional expanders is the fact that many interesting Markov chains actually come from high-dimensional expanders, and we can use high-dimensional expansion to analyze their properties or show fast mixing. One example for this is the celebrated work about matrode basis sampling using high-dimensional expanders. This is, of course, only a partial list. Our construction is actually a randomized algorithm that constructs bounded degree high-dimensional expanders based on one initial high-dimensional expander. This is an algorithm that's similar to a work by Bilou and Lineal, which constructed an infinite family of expander graphs using one initial expander graph. So our algorithm will take as input some initial x0, which is a high-dimensional expander. In addition, though, it will also take as input some infinite Cayley graph together with its finite generating set. Not any Cayley graph will do. This Cayley graph needs to have special properties. However, Lubotsky, Samuels, and Vishne, in their previous work of constructing high-dimensional expanders, actually showed that these Cayley graphs exist and explicitly described them in their construction of high-dimensional expanders. The output for our algorithm will be a bounded degree family of beta high-dimensional expanders, let's call them y1, 2, 3, and so on, which will have the following properties. The first member of this family will actually be a sparsification of this x0. It will have the same vertex and edge set and a subset of the triangles. The links in y1 will be sparsifications of the links in x0. However, the sparsification will be done with respect to neighborhoods inside this Cayley graph. If the neighborhoods in this Cayley graph will mix, then so will our links be a good expanders. The final property of this construction is that all these y2, y3, and so on will be covers of y1. We will describe what this means in a second, but essentially this implies that neighborhoods inside yn will be isomorphic to their corresponding neighborhoods inside y1. This will give us expansion and bounded degreeness almost for free. So what is a simplicial cover? Suppose we have two simplicial complexes, x and x tilde. Simplicial cover is actually a map from the vertices of one simplicial complex to the other that has the following three properties. First, it is surjective. The second is that it is a homomorphism, namely every triangle in x tilde will be sent to a triangle in x. The third and most interesting property is the local isomorphism property, which states that if we restrict this psi to a link of some vertex in x tilde, this will be an isomorphism between this link and the link of the image of this vertex. So, for example, if we look at this covering map here that sends A0 and A1 to A, B0, B1 to B, and so on, and we look at a link, say the link of V0, it looks like these two edges, and psi sends it to these two edges. So the links are isomorphic. The same for B1, and actually for every vertex here. So, as we said before, the construction that we have will have this property where these yn's will all have covering maps to y1. So this in particular will give us bounded degreeness because the degree of every vertex in Yn, which is the size of the link, will be at most the maximal degree of a vertex in Y1. Also, of course, this will give us link expansion just by graph isomorphism. For the rest of this presentation, I want to tell you how this algorithm works, but we will have some simplifying assumption. So we won't want to output an infinite family of covers. Instead, we will just output Y1 and a single cover Y2. For this, we actually won't need an infinite Cayley graph, so we can describe all these ideas in an elementary manner, but the main ideas of the algorithm will still be conveyed. To understand what the algorithm does, let's go back to the work by Bilou and Lineal and understand how they constructed graph covers. Given a graph G, and a labeling F on the edges of this G, and say this labeling has values 0 and 1, we can induce from it a graph cover, which is a graph whose vertices are two copies of the vertices of the original graph, and so that we connect the edges according to the labelings here. For example, if the edge BC has a labeling 0, we will connect the edges in parallel, B0 to C0 and B1 to C1. On the other hand, if the edge, say BA, is labeled by a 1, we connect the edges crossing. A0 goes to B1, B0 to A1. So from this 3 cycle, we actually got a 6 cycle. Bilou and Lineal used this technique to show that if G was an expander, then in fact we can construct infinite families of expander graphs using random covers that are constructed by taking these random Fs. However, notice that if this were not a graph, but actually a higher dimensional simplicial complex, then if we had this triangle here, we couldn't have put it anywhere in this cover. So this gives us graph covers, but not simplicial covers. However, and this is well known to people that know some algebraic topology, it turns out that the labeling also induces a simplicial cover if and only if the sum of edges on every triangle sum up to 0 modulo 2. So as you can see in this example at least, if this A, which is mapped to this A0, has 2 crossing edges, then the third edge should be in parallel so that this triangle could close. This is the reason that this labeling needed to be 0 if these 2 were 1. So note that we started with this labeling and then we could have deduced a double cover like this. However, one should observe that this cover, and indeed this is many times the case, is actually a disconnected cover. And it turns out that this is an inherent barrier to this technique. And in fact, many simplicial complexes, including for example the complete complex, actually don't have any connected cover. So all covers will look like these disjoint components. So there is no hope to sort of extend Bilou and Lineal's idea to randomly sample this thing and create a cover for our initial X, because sometimes such covers don't exist. However, we should do sort of a converse to this idea. We will start with a simplicial complex and we will randomly sample a labeling. However, instead of trying to sort of fix the labeling so that it will sum to 0 on every triangle, we do the opposite. We take all triangles that do not sum up to 0 modulo 2, like this middle triangle here, and we just remove them from our simplicial complex. This will essentially be our sparsified simplicial complex Y. After this, hopefully, because we have removed triangles, this will somehow positively affect the connectivity of the cover of Y. And indeed, this will sort of be our algorithm. However, there is a minor problem here, that the connectivity of the links could, of course, get hurt from removing triangles. For example, previously, this B had a link which was a path, but once we remove this triangle, it corresponds to somehow removing edges from the link, which may hurt the connectivity of the link. So our algorithm will actually do the following. Given some input X, we randomly sample a labeling F from the edges of X to 0, 1, and let us denote by T prime the sparsification according to this labeling, namely all the triangles such that f sums up to 0 modulo 2 on the edges of the triangle. Now, let's denote by y1 the simplicial complex that comes from this sparsification. But now, instead of just outputting y1, we will do this while loop that goes over all the vertices one by one. And if it sees a vertex which is not a beta expander, it will just resample the labelings of the edges that correspond to triangles that touch this vertex. So we start by arbitrarily looking at the vertices one by one. Whenever we see a vertex that's not a beta expander, we resample the edge labelings, and of course this corresponds to resampling this t prime and resampling this y1, which is the sparsification. This is a while loop, so in particular it may not halt, because it could be the case that we resample the link of u, we might have ruined the link of, say, v. So now, after this, we will again go over all the vertices, and maybe we will resample the link of v, and we could have ruined again the link of u. So this is a while loop. We will show later that indeed it halts, and when it does, we will output y1, and y2 will just be its connected cover. So this is basically the algorithm. Of course, we should ask ourselves, why does this a priori infinite while loop halt, at least with high probability? Also, we should ask ourselves, why does this y2 actually become a connected cover and not be disconnected, just as we saw before? So, unfortunately, I can't prove to you that this algorithm indeed stops, but I will say, just as a comment to the expert, that the proof is based on a very beautiful result by Moser and Tardos, which is called the algorithmic Lovász local lemma. Essentially, this says that even though the links could be non-expanding with some probability, this probability is rare enough and independent enough among all links such that eventually this fixing process in the algorithm will halt. Similar techniques will also assure us connectivity of y2, at least with high probability. Finally, after we saw what this algorithm does, we should ask ourselves, how could we use this to actually produce an infinite family of high-dimensional expanders? One thing that won't work is the naive approach, namely that we could just use this sparsifying algorithm again and again. So, maybe we start with some x0, we use our algorithm to get y1 and y2, and then maybe we take y2 and put it as input to our algorithm to get y3 and y4, and so on and so on. The reason that this won't work is because we are actually sparsifying the links. So if, for example, initially a vertex here was connected to, say, m triangles, after this sparsification, every vertex will be connected to, say, roughly m over 2 triangles here. And the same will happen every time we iterate this algorithm. So eventually, either the links will be empty or something else will happen which will be bad. This approach won't work. So here actually is where the infinite group that we take as input comes into play. It turns out that if we sample labelings that are not in the set 0, 1 or Z2, but instead are in this generating set of this infinite Cayley graph, we can essentially get for free from one labeling an infinite family of covers to our sparsified simplicial complex. The analysis of the simplicial complex will be quite similar to the analysis of the first one, but somehow we will get, instead of one cover, an infinite family of finite covers. However, this of course alludes to the following open question. Can we actually construct high-dimensional expanders without using any scary algebra or any very involved groups? Thank you for listening.